In this video, we're going to keep talking about substitution. So this is substitution part 2. So if you haven't watched part 1, you may want to go watch that one first. So substitution is a sort of primary technique for integration, or taking antiderivatives, and specifically it's meant to counteract the chain rule in derivatives. So let's go ahead and just dive right in and do one with definite integrals, which we haven't done yet. So we can sort of see that this is a classic chain rule problem. We can see that this is a composite piece, right? We've got x cubed plus 1 being squared, and you can probably see if you've done many substitution problems that the sort of derivative relationship is very clear here, right? If I take the derivative of x cubed plus 1, I should get 3x squared. So that is in fact what we're going to do. So let's go ahead and set this up. So we identify our composite piece, right? The inside of our composite piece, we're going to call that u. We take du, which is 3x squared, dx. Don't forget the differential that goes with this. It's very important that you have to replace the differential in the original. So we know that this is going to be something, and we don't know what goes here yet. But we know that the 3x squared and the dx, those get taken care of by du. And then x squared, or x cubed plus 1 being squared, that's just going to be u squared. Okay, so this is going to be a very straightforward integration problem. Now the issue is, what happens with these? And the answer is, these are values for x, right? So remember, this whole process of u-substitution is switching your old variable for a new one that's related to the old one. So our original variable is x. We've rewritten these functions in terms of a new variable, u. So these are x values, so what you need to do is replace them with values that correspond to the new variable. Just like we replaced these functions in terms of our new variable, you need to replace these values in terms of our new variable as well. So specifically, we're going to calculate u of 1 and u of 0 and see what those values are. So u of 1 meaning I'm going to take u, which is x cubed plus 1, and I'm going to plug in this value for x and see what I get for u. Right? So in this case, I'll get 1 cubed plus 1, or 2, and here I'll get 0 cubed plus 1, or 1. So my new integral is from 1 to 2. So just like I replaced all these pieces of the function that used to be in terms of x with u, I also replaced my upper and lower limits, which used to be in terms of x, with their new corresponding values for u. So now I've taken this, which looks kind of complex, and replaced it with something extremely straightforward if you're familiar with, the very basics of antidifferentiation. So this should be 1/3 u cubed, evaluated from 1 to 2. So I'll get 1/3 2 cubed minus 1/3 1 cubed, or 8/3 minus 1/3, for a grand total of 7/3. Okay, so this is sort of what's new in this video so far, is if you've got upper and lower limits, don't forget to change them to the new variable as well. Okay, so now let's look at another one that's a definite integral, so we can see what happens, but also something that involves just a little bit of trickery compared to some of the straightforward ones we did in our first video. Okay, so first this one, note, it's not immediately asking you to evaluate an integral, it's giving you context. So find the area under the curve for this function over some interval. Okay, so the first thing you have to know is that the area in question is what integral, and you may pause and set it up yourself. But it's the integral from 1 to 3 of the function in question, right? That's what the integral symbol is supposed to mean. That's how we sort of built the definition of a definite integral, right? As limits of Riemann sums, which are area under the curve. So now the question is, evaluate this integral. Okay, so again, you may pause and try to sort of see what you think the right u-substitution is and how this is going to go. Okay, so using our guidelines for choosing u from the first video, we have a denominator. Usually things in the denominator are a good candidate for u, so we'll try x squared plus 1. That's going to make du 2x dx. And if I rewrite this fraction, I see that I don't actually want 2x dx, I just want x dx, right? This is what I'm trying to take care of with my differential, because this will be easy to replace with u. But luckily that's an easy fix, right? I've got 2x dx, so I can just divide both sides by 2, right? And get, oh, well, x dx, that's going to be 1/2 du. So you often have to adjust by a constant here when you do u-substitution, but that's not a big deal. And then also new in this section, right, is that I have my upper and lower limits to contend with. So I also need to figure out what's u of 3 and u of 1, my old upper limit and my old lower limit. So if I take 3 and plug it into u, right, I get 3 squared plus 1, so 10. And if I take 1, I get 1 squared plus 1, or 2. So my new integral that involves u is going to be the integral from 2 to 10. 1 over x squared plus 1 becomes 1 over u. And x dx becomes 1/2 du. And the idea is that this area is the same as this area, right? And I've just replaced this problem, which looks more complex, with one that's hopefully more straightforward. So this becomes, right, I can take that 1/2 out, taking the integral from 2 to 10 of 1 over u du. So that's 1/2 natural log absolute value of u evaluated from 2 to 10, or 1/2 natural log of 10 minus 1/2 natural log of 2, or using rules of logarithms, right? If you do subtraction of logarithms, that's division inside of a logarithm. So 10 divided by 2 is 5. So 1/2 natural log 5 is the area under the curve. Okay, so again, we're doing definite integrals. That's relatively new. And then also this time we had to do this adjustment by a constant. Not too big a deal. This is sort of similar to the baby chain rule problems we were doing way back a few sections ago. Okay, now let's look at a sort of more substantial trick for u-substitution. Say I want to evaluate something like this. So I have x times the square root of 3x minus 1. So you may want to try this out and see what happens, if you want to pause. Okay, so using my guidelines for u, I do have a composite piece, right? I've got square root of 3x minus 1. So the inside of that is 3x minus 1, which means that du would be just 3 dx, right? Because I take the derivative of this and I sort of throw the differential on. Well, that's not quite as good as many of our problems have been so far. Okay, so for one, I don't have a 3 out here anywhere. I mean, I have this 3, but that's going to get taken care of by u. Okay, so I'm going to have to do that adjust by a constant thing like I did last time, because I have this dx that I'm going to need to take care of. Okay, fine. I can replace that with a 1/3 du. Let's just rewrite a little bit here. So this square root of 3x minus 1, that's just going to be square root u. Right? The question is what's going to go here. So this is square root u. This is 1/3 du, right? That's my differential here. But the question is, what am I going to do about this, right? Like in the past, usually the differential carries whatever we need, right? Like you have the composite piece and you substitute in for that, and the differential just sort of covers the rest of it, and in this case it doesn't. So you might, again, pause if you want to and ask yourself, how on earth are we going to fix this? Because we can fix it, and it's not too big a deal. What we're going to do is use the fact that u is equal to 3x minus 1, right? This relationship. We're going to solve this for x, and that's going to be what we put in for this x, right? So we can see that u minus 1 is 3x, or 1/3 u minus 1 is plain x, right? So when we go to do our original integral, this question mark is 1/3 u minus 1. That's what we're plugging in for x, right? This piece. Then this piece is all just square root u, and then this piece, right, is our 1/3 du. Now, you might be saying to yourself right about now, this does not look better than the original, right? Like the whole point of u-substitution is that you should get something that looks simpler. And in this case, it doesn't really appear that we did get something that looks simpler. But there's something important that we did do here. So first, let's just do some cleaning up a little bit, right? This 1/3 can get taken out. This 1/3 can get taken out. So I'll have a 1/9 on the outside. And then I've got u minus 1 times square root of u du, and I claim that u minus 1 times the square root of u is better than x times the square root of 3x minus 1, even though they look pretty similar in terms of difficulty. The reason it's better is because neither of these is a composite function, right? Like I've got this linear piece and I've got this square root piece, but neither of them is composite, right? As opposed to this, which has a composite piece. Square root of 3x minus 1, right? That's a composition of functions. Neither of these is a composition of functions, okay? Which makes them much more straightforward to integrate. So in particular, there's one little algebra trick that I need to use here, and then we'll be able to see pretty clearly how this should go. And that is, I'm going to take this u minus 1, and then I'm going to recognize that this is u to the 1/2 power, square root is. And then, right, because these things are not composite, I can just distribute this u to the 1/2, right? So this is u to the 1st times u to the 1/2 for a grand total of u to the 3/2 minus u to the 1/2 du. And now I can just use power rule for integrals. So this is 1/9. So when I anti-differentiate this, remember I add 1 and then divide by the new power. So if I add 1, I'll get 5/2, and then if I divide by 5/2, that's like multiplying by 2/5. And then similarly here, if I add 1, I get 3/2, and then if I divide by 3/2, that's the same as multiplying by 2/3. And then of course I have to add my constant of integration because this is an indefinite integral. Right, meaning I did not have upper and lower limits, right? There's nothing in these types of spots. So the last thing I need to do is I need to clean up these constants a little bit, and then also I don't want to leave my final answer in terms of u, right? So this ends up being 2 over 9 times 5 is 45, and then I have something to the 5/2, and this is 2 over 9 times 3 is 27. Times something to the 3/2. And then, of course, to see what u is, you just go back and see what was your original substitution. You know, we see it written in 2 places here, but u equals 3x minus 1. That was our original substitution. So this is a 3x minus 1. This is a 3x minus 1 as well. So this is another sort of trick that sometimes you have to employ when you're doing u-substitution, right? You've got these sort of composite pieces, and sometimes you have to do like this kind of switch and solve for the variable. It's worth noting here, maybe I should just comment, you only ever have one of plus c, or evaluate from like 1 to 2 or a to b more generally, right? So if it's a definite integral, you do not need plus c, right? So like if it looks like this, then when you take the antiderivative, you end up with this. If you don't have these things, right, if they're blank, then you end up with a plus c when you take the antiderivative. So this is more on substitution.